dielectric medium. So we cannot use this one because it's not a direct current source. All right, so with that, we will go to today's lecture, which is about conservation of energy and conservation of momentum in electromagnetic field theory. Last time we were able to find the conservation law for energy so this is what we determined last time. So this is we saw this is the electromagnetic energy in the field, which is conservation of energy in electromagnetic field theory. So that we say dW by dt, that's the rate of work done equals to the rate of change of energy in the electromagnetic field EM with respect to time. Yeah, U. Minus, with the minus sign of course, over a closed surface integral S of the Poynting vector dotted dA. We said S, the Poynting vector, vector S is given by epsilon naught times the integral of the electric field. Not the integral, it's just E crossed with B. It is 1 over naught. Yeah, 1 over mu naught. Yeah. So it's going to be 1 over mu naught E crossed with B. And we say, it's basically is what you learn as an intensity in introductory physics. It tells you the amount of energy per unit area, per unit time, that's leaving a certain volume of charge. So we will see the application of this conservation law using an example, a simple example, which you can find the rate of energy delivered to the system with respect to time. So basically, this is what I'm talking about. If you have a cylindrical conductor of length L and radius A, is connected to a direct current power supply, which generates a voltage V and a current I. So find the power delivered by the source using the Poynting vector. But without using the Poynting vector, if you want to find the power, what's going to be the power? The power delivered by the source is going to be just the voltage times I squared R. That's if you know the resistance. Here you have a power source which supplies the voltage V and generates the current I. So it's just a product of the two. But that's from just when you that's what you learn in intro physics, right? But let's apply what we learned here. So you apply a voltage through a conductor that has length L and an area A. So that voltage creates an electric field. So you have an electric field. And you have a current that flows through this conductor. So a flow of current, a flow of charge which generates the current produces a magnetic field. So we have an electric field and a magnetic field. So from our conservation law, these fields carry energy. So let's apply this and find the power delivered by the source, which is equals to the voltage times the current. So first, what's going to be the electric field? Example 3.1. So what you have is this conductor of length L and area A. So the area of this is A.
Radius.
Oh yeah, radius A. Yeah, so this is the radius R equals to A. And it's connected to a power supply, a direct current power supply. So you have a flow of current and a voltage V. So what's going to be the electric field inside this conductor? The electric field, if you know the potential difference between these two surfaces, what's going to be the electric field? Yes, so that would give you the electric field is going to be whatever potential difference you have V over N. So in vector, if I use cylindrical coordinates, which means let me say that this is the z-axis, okay? Just rotate the coordinate system, and this one is going to be x cross.
So y would be in control.
Yeah, okay. But if I put that one into y, x cross y, so x is going to be outward here. So that's going to be x. So the electric field then, if this is the plus in, so this is going to be plus, and this is going to be minus, right? So the electric field in vector notation is going to be along the negative z direction. Now, what about the magnetic field? Well, to find the magnetic field, you have to know that you have a current that's incident over this area, all right? So we are interested in the magnetic field inside this conductor. So you just consider the usual Amperian loop at the radius S. So if you consider this Amperian loop of radius S, then you can simply write the magnetic field. So you can tell me that we don't have to derive it at this stage. The magnetic field B first is going to be in what direction? So you have a current going from this end to this end, so that is going to be in plus or minus V? Yeah, negative. So that's going to be mu naught I over, that's I enclosed, over